Hello and welcome to this presentation on optimization in business. My name is Chris Russell, and I've been working with the application of software to business problems, primarily in the business and logistics area, for the past 3 decades or so, and wanted to share some of the insights that I have gleaned. My role typically has been the person who needs to take technical topics and bridge the gap, build bridges to the business problems that they solve. So this is one practitioner's accumulated story of some of the most common forms of optimization and the pros and cons of how optimization is applied in the business world. I put together this presentation to provide a primer on what optimization is in general, why we do it in the business world, and some specific instances of application of optimization in programming. I'm not a mathematician, but I've worked with, implemented, and sold many of these optimization methods in business software over the last few years, and I'd love to connect with you as well. Feel free to shoot me an email or connect with me on LinkedIn. So let's get started. One of the important things to realize is that optimization as a term is used rather freely in industry. But in mathematics, optimization means a specific thing. We tend to use the term optimization fairly loosely to describe any type of problem solving. But to a mathematician, they mean find the best answer to a specifically designed problem. Not a good answer, but the best answer. So, the real message here is understand who you're talking to and what question they're really asking. If it's a math geek or an operations research PhD, they may be asking a different question than the manager of the shipping department, for instance. The other thing that should pop out at you is that in order to find the best answer, you have to define what best means. Is it lowest total cost? Is it shortest distance? Is it highest fill rate? What exactly are we trying to optimize? As a business professional, we aren't really trying to solve pure math problems because we like calculus. We're trying to solve business problems. And the value we provide is that we help build a bridge between the business problem and the math. This bridge, this value add, can be called a model. A model allows us to represent the business problem in a way the business users understand, but also in a way that software and programming can convert to numbers that can be crunched by the mathematical optimization. Without the user interface, the data, and the model, you'd have to type ones and zeros into the CPU. The model is that bridge. The ability to model the business problem in an understandable way is a significant enabler to the business. One of the challenges that we run into is that everyone thinks computers are magic boxes. You pour your data in one side, a miracle happens, and answers to your business challenges pop out. Computers are really good at processing large quantities of numbers and millions of rote calculations, but they're not magic. Culturally, we have been conditioned that Moore's Law means that today's computers can solve any problem instantaneously. Someone is always telling that story about how your iPhone is 10 bazillion times more powerful than the first IBM mainframe. Yes, computers are thousands, if not millions of times faster, but these problems, these optimization problems, are still hard. There's no magic to it. The types of problems we're optimizing are not simply find the lowest cost. They are find the lowest cost and the highest profit and the highest cumulative customer satisfaction over a 3-year horizon by looking across the entire business and taking into account the thousands of real-world constraints that we have. These are hard problems with mutually exclusive optimization goals and trade-offs. Yes, computers are super awesome and good at math, but the problems are still hard. And you can't just dump data into the model and expect magic answers. That's why our ability to model the business and to help determine what you're trying to get out of the optimization is so valuable. Often, you will get an optimization question in the form of, how fast is the optimization? Which, like all good consultants, we answer, it depends. We're not avoiding the question. It really does depend on the size of the problem and how constrained it is. Our value add is in understanding what the business needs to get out as an answer to run their business, and then helping them model the problem in such a way as to provide those answers, those results, in a time frame that is useful to them. Inevitably, inexperienced modelers will try to cram their entire world into a single model and flip on all the constraints, and when they hit the button, it doesn't solve. The theory is that the more you put into the model, the better the answer you'll get. We call this trying to boil the ocean. What happens is you don't get an answer, or you get an answer you can't understand or use. Again, the question of how fast is the wrong question. Understand the answers that you require and then configure the model in such a way as to get the best answers for that problem given the constraints. Another term you'll hear used when talking about optimization is solution space. This simply means determining where you're going to look for an answer. If I asked you what's the best diner in Ohio, what is the solution space I've defined? Well, it's Ohio. In optimization, this means mathematically defining where you're going to look. You can't look everywhere because that would leave you with infinite choices. Even true mathematical optimization that finds the best answer is only finding the best answer for that defined solution space. In business, the solution space might be defined as appointments next week or planned work orders for the next 6 months. The solution space can be further constrained or narrowed by saying things like in lot sizes of 12 or more, or within a driving time of less than an hour, or within a 30-mile radius. So why do you care? Because the definition of the solution space is one of the major contributors to the performance of the optimization. This is another example of how experience and expertise can be used to help you model the appropriate way to get the most business value out of the optimization. People are hardwired to like stories, so I'm going to give you a simple, down-to-earth story you can tell about optimization. Here's your story. How many of you like to build jigsaw puzzles? I like to build jigsaw puzzles. Every summer, when I'm on vacation at my house on Cape Cod, I build a 1,000-piece jigsaw puzzle. Now, if I wanted to build a puzzle by testing every combination, how many different combinations would I have to try? This is an optimization problem. A mathematical optimization purist would say that you really can't be sure that you've built the best puzzle unless you've tried all the combinations. And the math is fairly simple. If I have 2 pieces, each with 2 female and 2 male connectors, I can do that math in my head. That's 8 different possible combinations. 3 pieces would be 24 possible combinations. And you may remember from math class that this is known as a factorial. The number of combinations for a set of 3 is 3 times 2 times 1. For 4 is 4 times 3 times 2 times 1. But you notice in the table here, when I get to 10 pieces, there's over 3 million possible combinations. When I get to 100, it's a number that has 158 characters before the decimal point. And when I get to 1,000 pieces, the number is so large it blows up Excel. This is what we are asking computers to do when we optimize. This is why modeling and determining the constraints in the solution space is so important. We're answering the more important question of what should we be optimizing in the first place? But Chris, you say, it only takes a couple hours to do a jigsaw puzzle. How is it possible if the math is so hard? Well, in reality, when I'm solving the puzzle, I just want to put it together without any extra or missing pieces. I don't care about trying all the different combinations. I actually want to minimize the number of combinations that I have to try. And I know when I do a jigsaw puzzle, the first thing I do, I sort out all the edge pieces, the straight pieces, and put them together to create an outside frame of the puzzle. And guess what I just did? I just defined the solution space. Then I use rules to sort out the different colors and shapes that are easy to identify and give me cues to which pieces go together. In mathematical optimization, these rules are known as heuristics. For example, find all the pieces with red tree leaves. Find all the house pieces. Then, and only then, will I brute force solve the parts with no visual cues by trying all the different combinations. In business optimization, we do the same thing. We don't want to try all the combinations. We want to get to the best answer as quickly as possible. We use business rules or heuristics to direct the optimization for efficiency. What kind of optimization do you use? That's a hard question. There are hundreds of mathematical optimization techniques. I'm going to review a handful of these that are common to business systems. Many of these methods have been around for years. Here's what you need to remember. There's nothing inherently good or bad about different optimization methods. It really depends on the problem you're trying to solve and the way you apply those algorithms. There's no magic optimization pill that solves all the problems. Don't take that baloney from the dogmatic optimization purists that you're going to run into. Let's start with heuristics. Heuristics are by far the most common form of optimization in business. Heuristics are business rules. They approximate the way people do the work. Find the least expensive approved shipping method. Find the shortest lead time. These are tasks that used to be done manually or with spreadsheets. Heuristics do them better, faster, and more robustly. Heuristics most exactly match the business processes that we are challenged with in business. What's the rub? Why do people say heuristics aren't? Pure mathematicians will argue that heuristics don't find the mathematically best or optimal solution and therefore can't be referred to as optimization. Dang it. What they do very well is quickly find answers to very large transactional questions. By taking advantage of existing business expertise, like when we made the puzzle, the answers the heuristics find are feasible. This means they obey all the business rules. Heuristics are fantastic for highly constrained business problems like planning and transportation. So don't let math geeks tell you heuristics are bad. Why would you try every combination in the puzzle if your goal is to make the puzzle, if you don't have to? So next, let's talk about linear programs. Linear programs, very common in business. Linear programs simply means that you're modeling the problem using equations that are lines. Remember, in school, you learned that the equation for a line is y equals mx plus b? Well, linear optimization creates a gigantic matrix of these equations and solves it by brute force. This giant matrix of line equations is chunked through and reduced to one best answer. In this sense, you get a mathematically optimal solution. Because it is doing a brute force solve, though, linear optimization takes a lot of computer power. And if you make the model too big, it takes forever. This is why linear programming is typically used for strategic, aggregate, and long-term problems where you can let the solver run for a long time and use a higher level of aggregation in the data. So linear programming historically has not scaled well, and users have been required to aggregate the data to get an answer. So anyone who tries to tell you they're using pure LP to solve operational business problems is probably full of you-know-what. Those are not linear problems. Tiered pricing, lot sizes, many other heavily constrained problems can't be modeled as a linear equation. To solve these problems, linear-based solutions are forced to either approximate these constraints, i.e. take a squiggly line and make it into a straight line, or they pre-process and post-process the problem with heuristics and only solve the parts of the problem in the middle with the linear program. So there's some buzzwords around this: simplex, cplex. These are different flavors of linear programs and commercially packaged linear solvers. The good news about linear programs is there's a lot of commercially available prepackaged linear solvers you can just plug into a problem. Quickly, we'll talk about integer programming or mixed integer programming. And this is an optimization technique that simplifies the problem by assuming the numbers are integers. And it's typically one of the approximation techniques that is used in combination with linear programming approaches to scale to more complex or larger problems. Another interesting approach is known as dynamic programming. Dynamic programming takes many-to-many relationships, like in a business network or bill of material, and it breaks them down to their component parent-child relationships, like reducing a bill of material or a sourcing network to each parent-child relationship. Then the dynamic programming rigorously solves for the optimal solution, and then once it has the answer, it iterates through the network to propagate that answer up and down the chain, the network chain. And this is known as a spanning tree to pure mathematicians. This is a very good way to solve stochastic, which we'll talk about in a little bit, and multi-echelon network problems. And dynamic programming does require some care in your modeling and some advanced understanding in its application. And the last method I'm going to talk about is genetic algorithms. So genetic algorithms are super cool and sexy. So think of Darwin's theory of survival of the fittest. A genetic algorithm randomly selects solutions from a broad solution space and tests them against a fitness criteria. The strong solutions survive, and the weaker ones get killed off. The algorithm will continue to mutate and try different combinations until you turn it off. Genetic algorithms are great at combinatorial and sequencing problems. Genetic algorithms avoid what's known as a seed bias by starting at a random point. Genetic algorithms find non-obvious solution spaces through mutation, and so they avoid being trapped into local minima or suboptimal solutions. So the downside is that you never really know if you have the best answer, because they'll run forever if you let them, and they'll keep trying different mutations. And like a linear program, you may need to pre-process or post-process heuristics to apply the genetic algorithms in a highly constrained environment. One of the things you'll hear thrown about in the business world is deterministic problems versus stochastic problems. And how does this apply to optimization? Well, deterministic and stochastic they're different ways of looking at a problem. Deterministic is like a calculator. It's using set numbers as an input to determine discrete answers, like how many screws does this plate assembly need? That's a deterministic question. Stochastic takes into account uncertainty. This is important because most business problems have some randomness to them. Stochastic approaches allow us to come up with probability ranges for expected results, like how long does it take to get to the airport, or when will this assembly fail? These are stochastic questions. So in summary, many times, technology-minded folks will trot out optimization techniques in an attempt to dazzle business people. But optimization is not magic. It's just another tool set you can use to address business challenges. And it's important to know what problem you're trying to solve, the appropriate way to model that problem, and then apply the appropriate math to get the answer you're looking for in the time you have to get an answer. So thank you for the gift of your time. and good luck in your optimization pursuits. And I'd be honored to connect with you if you'd like. Cheers.